Right now we are discussing receiver, right? We discussed from modulation all the way to the demodulation, also up to the equalizers, right? So the last thing that we are going to discuss is the detector or the decision block, which is the last block at the receiver, right? So in order to understand the basics of receiver or the detector or decision-making block, we need to understand the basic theory, like a probability theory. Okay. The reason that we are discussing this is because that let's suppose we are transmitting BPSK symbol. Right? We transmit BPSK at the transmitter. So which means that we originally start from 0 or 1. And eventually you do a BPSK modulation. So you're going to transmit either S0 or S1. Right? S0 is going to be a positive cosine. S1 is going to be negative cosine. That's a BPSK modulation. Right? So you transmit all the way, and we have the channel. At the receiver, this is receiver, we have a demodulation here, demod. And then eventually you have an equalizer, something like this. But eventually we're going to make a decision. After the decision, you're going to decide either 0 or 1. So we're going to recover the bits, original bits back after the decision. But what is the input to the decision here? The input to the decision block right here, the input is going to be some number, let's say it's R. Let's call that R. So this is going to be some number like R. So for example, right, let's plot the S0, S1. This is symbol, right? So the best way to present the symbol is to use the constellation plot. So we're going to draw the constellation plot for this S0, S1. And you know the S0 corresponds to here in the constellation plot, and S1 goes to here. We know that, right? Because this is cosine plus cosine, this is minus cosine. So this is what we transmit. But because of the noise in the channel, also because of the all this symbol interference, all this multipath, all this fading, all of those things, eventually even after demodulation and even after the equalizer, what you're going to receive here is not going to be perfect like this. Here, what you're going to receive, again, we can plot that in constellation plot. So if you plot the R in the constellation plot, R probably goes in here somewhere, or maybe here, or here, here. It can go anywhere, basically, right? You transmit S0, for example, right? So you transmit this one. So everything, if everything is perfect, no noise, no fading, no ISI, then you transmit S0, then you need to receive here, right? Because everything is perfect. But unfortunately, nothing is perfect. And because of all this ISI, all this noise, eventually what you're going to receive is any random point. It can go anywhere. Okay, let me make it a little bit clear. Let me draw equalizer here. And then decision. Okay, so let's say let's call here as R. Here let's call here R1, R2. Let's make it differentiate, R0 and R1, just to help you understand better. Okay? Once you do demodulation, right, the R1 can be really random. So if you plot this R1 anywhere, if you plot the R1 in the constellation plot, this R1 can go anywhere. It's purely random. It can go anywhere. Because there is the ISI, because of interference and all these things, and also noise. But once you go through the equalizer, Now the output of the equalizer would be R2. And if you plot this R2 in the constellation plot again, hopefully what we're going to do is we're going to get this kind of plot. So this one completely different, right? This is exactly the symbol you receive after the modulation. But this symbol R1 still has some interference, like intersymbol interference. So that's why this symbol can go random. You transmit S0, but you receive as this point. You transmit S1, but that is received by this point. Something like this, right? So if you transmit like 1,000 symbols, all these 1,000 is going to be, each of them is S0, S1, right? Maybe S0 500 times, S1 500 times. That's how you transmit 1,000 symbols. But still, when you receive 1,000 symbols, you're going to get the 1,000 points randomly distributed in the constellation plot in R1, right? But when you put this one in equalizer, this equalizer will remove intersymbol interference. Not completely, but somehow. You reduce the impact of interference. So therefore, in R2 here, again, you plot the constellation plot, then you're going to see this kind of picture. So compared to this picture and this picture, now you can see that this picture still this is completely dirty, but this picture is not so clean, but at least better than this one. Okay, this one at least you are just making group, right? All this here there's no group; it's completely random. But in this case, at least some of the points move on to left side, and some other points move to the right side. So you can see some of the groups. Still, there are some points in the middle, like this. Still, there will be some points, but most of them are grouped like this, left or right. So that's what you're going to see here in R2. So what is R2? Each one of these points is R2. So what is the value of each one? Let's say original one here, S0 is going to be like +1. Of course, you have cosine, but let me drop the cosine carrier. It's going to be -1, right? That's why you have here. This is +1, this is -1. What about R2? R2, again, can be this value, for example. For example, this value. What is the value? In complex value? This value may be like 0.85 plus 0.3j. Something like this, right? This is just an example. So you're going to get this kind of value here in R2. This constellation plot is simply to visualize, simply to illustrate what you're going to receive at R2. This decision block now need to make a decision. And then you need to convert each one of these dot, each one of these symbol, receive symbol, into either 0 or 1. So you're going to convert each one of these points into 0 or 1, right? So that's what you need to do in the decision block. So how would you change? Let's say you receive this one. Would you make it as a 0 or would you make it as a 1? So that's the decision you need to make. So this is going to be 0 or 1. Maybe you can say 1, right? Why? How do you know this is 1? This is based on probability. Everything is based on probability because here, the point that you receive is a random, but probabilistic point, okay? It's more probable that this one can be decided to 1. This one is more likely. This is based on probability. So that's why what we are discussing here is all probability theory. We are discussing this block right now. We are talking about this one. And your goal is you receive this kind of symbol as the input. Okay? Input to the decision block is like this. Now what's going to be the output? 0 or 1. So that's the output. Now the question is, how would you make a decision you're going to receive this. Would you make a decision with a 0 or 1? And why you make such a decision? So that's what we're going to discuss. So to do that, we need to understand the probability theory. And in probability, there are two different probabilities. We have probability called the prior probability, and there is a posterior probability. So prior probability basically means that it is the probability that you already know, or this is the probability that you can easily figure out. So for example, right, when you throw the dice, you know that the probability that you're going to get 1 would be 1/6. If the dice is correctly made, then it's going to be 1/6, right? So this is the probability that you already know, even before the thrown dice, right? You already know that. That's a prior probability. Posterior probability basically means that it means post, right? You can find out later. So that basically means that if some event B happened already, okay, and given that, what is the probability of A? So this is a conditional probability. So that's what we call as a posterior probability. So the probability of A, given that B event already occurred. Okay, so that's the posterior probability. So based on those definitions, what we need to understand is we need to remember this Bayes rule. Simply this equation. Okay, we need to remember this one. This probability, this rule basically tells you that when you compare these two, right, you basically reverse the A and B. So this is the probability of B given that A happened. But here, right in the right side, you see that the probability of A given B, right? So which is reverse of this. So that is on here, multiplied by PB, divided by PA. So that this probability is same as that probability. That's the Bayes rule. Okay? That's the Bayes rule. And the reason that we are discussing this Bayes rule is that the event A and B are not same. Okay? We'll see that in the next slide. But typically, we want to find out this probability. A already happened, and we want to find out the probability of B. But this one is very difficult to find because this is a posterior probability. Okay? Something already happened, and we are going to find out later. So that's typically it's difficult to get because it's like a back to the future kind of thing, right? Something already happened, but later we're going to find out what was the probability happened at that time, right? But this case is a little bit easier because A already happened and then B happens later, so that's a little bit easier to get. So we are basically switching those two. So this is easier to get. So that's why we use this Bayes theorem or Bayes rule. Bayes rule, Bayes theorem, all the same thing. This is same as the equation that we just looked at in the previous slide. I just changed A and B into H and D. Okay, same thing. So this Bayes rule is used in many different subjects. In statistics, they also use this rule. So here, D is the data, and H is hypothesis. Okay? So you have a data, and based on the data, you're going to make hypothesis. Okay? That's what that means, right? Given the data, you're going to make hypothesis. But typically, this is difficult to calculate. So instead, what they do is that if you already make some hypothesis, then you can get the data out of that. That's a little bit easier to get, right? And then multiply the probability of hypothesis divided by probability of data. So in order to understand this relationship, this is the example that we discussed last time, right? Let me change each one as because this one looks like difficult word. Let me change this as easy one. So what is the probability of getting cold? What is the probability of getting cold in the patient with a cough? So that basically means that you're a doctor and a patient comes to you and say, oh, I have a cough. So based on that symptom, that's a symptom or data, right? So the patient says, I have a cough. So based on that symptom, you are a doctor, so you need to make a decision. So in order to make a decision, you need to make hypotheses. Like this one, for example, right? This is the symptom, or this is the data. Data or symptom, same thing. So this is the data. Like this data is given to you, and here you need to make a decision. You are a doctor, for example, right? You need to make a decision. And in order to make a decision, you need to make hypotheses. In this case, there are two hypotheses. 0 is one hypothesis. 1 is going to be the other hypothesis. Okay, you make two different hypotheses, and given the data, based on this data or symptom, you're going to make two hypotheses and calculate the probability. What is the probability of, let's make this one as hypothesis 0. This is make hypothesis 1. So you're going to make two hypotheses, and this is the data, for example, right? Or symptom, let me say as S, because S means symptom. Same thing, data and symptom, same thing. So what you need to do here is that you need to calculate the probability of hypothesis 0 given the symptom. So the symptom is already known because the patient tells you, oh, my symptom is cough, I have cough. So this is given to you, right? You already, in this example, right, this is what you receive. So you already know this. You measured and you know that, right? So based on this symptom, given this symptom, what is the probability that your hypothesis H0 is true? So that's what that means. You need to calculate this one. Also, you're going to calculate this one. So given the S, what is the probability that H1 is true? So this is the probability is H0 is true. This is the probability that hypothesis H1 is true. So you need to calculate these two because you have two hypotheses. So for example, you calculate this, and let's say this one goes to 0.6, and this one, let's say 0.2. Then finally, based on these two calculations, finally you need to make final decision. So which decision would you make? H0, of course, right? Because this one has a higher probability. So everything is based on the probability. So that's what we are talking about here. Let's say a patient comes to you and say, oh, I have a cough. So that is like this. Cough is like symptom. So as a doctor, what you need to do is that you need to make symptoms. Oh, he has a cough. So maybe he's getting cold. Maybe he has some other disease, pneumonia, whatever, right? So you can make many different hypotheses, possible disease, right? Make some hypotheses and then calculate probability for each one. Okay, that is this probability here. That is this probability. So M means this disease here. So this is going to be hypothesis. So you're gonna calculate the hypothesis is 0 given symptom. If you have many hypotheses, then you're gonna calculate as many hypotheses you like. So for example, right, you have k different hypotheses, k plus 1 different hypotheses, then you're gonna calculate all these things. Because cough, maybe cough comes from cold, or cough comes from another disease. Another one, right? You have some other things. All of those things can be hypotheses. So you're going to calculate each one of these. Now the problem is that this each one of these, this particular probability is very difficult to calculate. Okay, let me ask you another way. So let's say this is given to you. You receive this one. And now we're going to calculate, we want to calculate this probability. So probability of H0 given S. So how would you calculate? How do you calculate this? Typically this you cannot calculate. You cannot calculate this one. Okay? Because this basically means that you receive this point, and what was the, given that, what is the probability of going back to S0? So that's very difficult to calculate. Same here, same here. If you have a cough, the patient has a cough, then what you're going to make is, oh, you're going to make hypothesis. Oh, he may be getting cold. And then you're going to calculate the probability of getting cold given the cough as a symptom, but this is very difficult to calculate. So I'm talking about this one, right? This one is very difficult to calculate. So what you're going to do instead is, in order to calculate this, what you're going to do is you're going to use that Bayes rule and change this into this way. So this one and this one is the same based on the Bayes rule, Bayes theorem. Bayes theorem. So Bayes theorem tells you that this one would be the same. But this one is very difficult to calculate. This one is much easier. Why is that? So let's think about this. First of all, this one is the probability that you receive this. Okay, forget the S0, forget the hypothesis. This is simply the probability of your getting this. That's PS. This PH0, this is the probability of hypothesis H0. Okay? This is simply hypothesis PH0. Now what about this one? Same way, we're going to change this into this way, right? Based on the Bayes rule, we are going to change this into that way. And then after you do this, right, what we're going to do is all these things. Okay. So all these things is like this. Eventually, what we're going to do is we want to calculate pH0 given S, and we also want to calculate pH1 given S. I'll put it here. pH1 given S. So eventually, we want to calculate these two, and we want to compare these two. Which one is true? Is it this is bigger or this is bigger? Eventually, that's what you want to do, right? We want to just compare these two. We calculate this one. We also calculate this one. And we want to compare which one has the bigger probability. If this one has a bigger, like a greater, this one is greater than this one, then what is going to be your final decision? Symptom H0. Hypothesis H0. That's going to be your final decision. So we typically write it this way. And if this one is greater than that, then our final decision is going to be hypothesis 1. So we typically write it this way. This is the basic rule for decision. So first thing is you're going to calculate these two. Okay, each one you're going to calculate somehow. Okay, somehow each one you're going to calculate and compare these two. Okay, so if this one left side is greater than right side, your final decision is going to be hypothesis 0. Which means that what is hypothesis 0 in this case? The final output 0. That's a hypothesis 0. And when you compare these to the right side has the higher or greater value than left side, your final decision is going to be hypothesis 1. So H1. In this case, it corresponds to 1. Right? So that's your final decision. So this is simply what you're going to do inside that block. Okay? Inside this decision block, this is eventually what you're going to do. Okay? Just remember this one. This is the most important thing in this block, in this decision block. Okay? But it's pretty simple, right? That's what you're going to do. Now, what you need to do, go into a little bit detail, what you're going to do is that this one is not easy to calculate. So therefore, based on the base rule, we're going to change this into this way. So let me change that based on the base rule. So once you change that, you're going to get this one. Same way on the right side, again, you're going to use the base rule and change that. You're going to get this. And then comparison, this is going to be same, H1, H0. So we can change this into this way by base rule. So using the base rule, we're going to change it to this way. Okay? So this is going to be the basic decision-making rule. Okay? You're going to apply. Now once you change that, we can simplify it. Okay, we can make it simpler. So let's take a look at it here. We're going to compare these two. Okay, which one is bigger? Which one? This one is greater, or this one is greater? We're going to simply compare. Since we are just comparing these two, actually, when you look at the bottom here in the denominator, we have a PS here, also PS. Both one has a PS. So we can cancel then, right? Because simply we're going to compare this. PS is on both sides, so it doesn't matter. So we can cancel this. Then we can simply compare these two. Okay, we can compare these two. We can simplify it this way. Okay, so that's going to be our decision rule. And not only that, if we make a certain assumption, like if here, if probability of H0 equals probability of H1, right? If probability of H0 and H1 is same, like this one, PH0, PH1 is the same, in that case, we can even cancel this, right? Because both are same. If that's the case, then it can even more simple. It's even simpler than that. Become this way. It becomes very simple. Now then, let's understand this condition. So what does this mean? What does this mean? PH0 equals PH1. What does that mean? That basically means that probability of hypothesis 0, probability of hypothesis 1 is equal. What does that mean? That basically means that we are transmitting with equal probability, half and half. We always make that assumption, right? Do you remember this assumption? You're going to make, if you measure a long time, like you transmit like 1,000 bits. Out of these 1,000 bits, maybe 500 would be 0, the other 500 would be 1. So that's this probability of equal probability between 0 and 1, right? So that is this one. So pH0, simply pH0 means probability of hypothesis 0. Simply that's what it means. And hypothesis 0 in our case is 0, bit 0. So probability of bit 0. And this one, pH1 means probability of bit 1. So that is this probability. So it's even we make this assumption, that assumption actually is okay, right? It's a valid assumption. Because in many communication systems, actually you are transmitting 0 and 1, equal probability, right? In most of the case. In most of the cases, 0 and 1 are equal probability. So this assumption is valid. It's perfectly okay. So once you make this assumption, then everything becomes very simple. And now our original decision rule was this one. Now based on these, we are going to change this into this one. So let's compare our original decision rule and our final rule. The difference is that we switch, right? In this case, H1 given S, here S given H1. So it's a switched, right? S and H0, S and H1 is switched in this case. Now let's understand this one. P S given H0. Okay, so let's think about, now we are talking about this one, or this one. So let's understand what's the difference between these two, right? Because the difference between these two is this one H0 given S, this is S given H0. So that's only difference, right? So let's understand these two. Let's first look at this one. This is our original probability, original hypothesis given S, original probability that we want to calculate. Again, simply the conclusion is this is very difficult to calculate. This is the original one we want to calculate, but this is very difficult to calculate. However, this one is relatively easier. Okay, much easier to calculate. So that's why we want to convert this one to this way. That's what we're doing here, right? This is typically very difficult to calculate. So eventually we, based on the base rule, based on the simplification, eventually we're going to change this into this way because this calculation, this probability is much easier to calculate. So let's take a look at what that means. This one, right? You already measure S, and then given that, what's the probability of H0? So that means you already receive S, and then you're going to calculate the probability of H0 and H1. So that's this one. What about this one then? This one basically means that hypothesis is already H0. Okay? We assume that hypothesis is 0. And then what is the probability of getting S? That basically means that you make some assumption of H0 already. So that means what is H0 in this case? 0 or S0. That is the H0. This one is H1, right? So in this case, what you're going to do is we basically simply assume that we transmit H0. Okay? Just make it H0. We transmit H0 because that's what we assume. Just transmit H0. And what is the probability that we are going to get this? That's this one. So how do you find out? How do you calculate this? This one, again, you just transmit S0 because that's what we assume. You just transmit S0. Forget H1. Just transmit S0. S0. Okay? Just transmit S0 and calculate the probability that you receive as S. The probability that you receive as this one. So that's what you're going to do. So this one is much easier to get because how would you get? How would you get it? You just transmit S0 and measure it. You measure it. What is the probability that you receive as this value? You can try it, right? Maybe you can transmit like 1 million S0 and just measure it. You can do that. But in this case, it's kind of reverse. You receive it already, and then now you are gonna guess what was the hypothesis. Okay, you already received this, and you're gonna guess, was it like H0 or was it like H1? Typically, that's very difficult to calculate. Relatively, this one much easier because in this case, we assume the H0 is the condition. So just fix it at the S0 and then transmit S0 like 1 million, 10,000 million bits. And then we just measure it. Okay? So that's why it is much easier. And then based on that, this one is calculated. Also this one, in this case, H1 is fixed. You just transmit H1. In this case, S1 is H1. So you just transmit S1 and then measure it. You know, what is the probability you receive as S? So these two is much easier to calculate compared to this one. Once you calculate each one, then you're going to compare and then and show you and see that which one has a bigger or larger probability. And once you decide that, you are going to make hypothesis, and based on that, you make a decision. It sounds like pretty difficult, but let's think about in our example, okay, of the whole things. So what we are discussing here is some of the basic theory behind this decision block or make this decision block. So let's take a look at this whole thing based on the example. Okay. What we're going to do eventually in this example is going back to this original goal, original decision rule. So this original decision rule is you receive as this one as an example. This is a receive symbol. So based on this receive symbol, you need to calculate either it's going to be hypothesis H0 or hypothesis H1. But this one is difficult. So instead, we're going to calculate this. So what you're going to do in this case is that you just transmit S0 and measure the probability of S1. So let's think about that case. Let's say you transmit S0. In this case, let's think about this way. Let's say our hypothesis is that these two, in this case, S0 corresponds to H0 hypothesis. That's what we do here. S1 is hypothesis H1. So we're going to do the same way. This one corresponds to hypothesis H0. This one is going to be H1. So that means H0, this one is going to be bit 0. This one corresponds to bit 1. Right? So this is going to be bit 1. That's the mapping. I'm talking about the mapping. This one is the mapping. Remember that every time we do a BPSK, there is a mapping, right? Bit to symbol mapping. Okay? So this is the mapping I'm going to use. When you have a bit 0, we're going to map it into S0, bit 1 into S1. Same way here, bit 0, H1, this one. Bit 1, we are going to correspond to hypothesis H1. Now, what you're going to do is, let's say you transmit S0. Okay, you transmit S0 here. S0 is +1. You transmit this. Now we have a channel, we have symbol interference. So once you transmit this one in the constellation plot, what is the probability that you receive? Let's say here is 1, here is -1. Okay? So here is S0, perfect S0. This is a perfect S1. It's the same as here. Now you transmit S0. Okay, you transmit this point. What is the probability that you receive as this one? That's this. No, that's this. You transmitted H0 or S0, and then what is the probability you receive as S, this point? So that's this one. Same way, now you're going to transmit S1, minus 1, this point. You're going to calculate this. You transmit H1, and what is the probability that you receive as S? So let's simply calculate these two. Which one has a larger distance? Larger probability in this case. So in this case, you transmitted H0, you receive as this. In this case, you transmit this point, and then you receive as this one. Which one has a larger probability? This one is a larger probability. How do you know? Based on the distance. In this case, based on the distance. If you transmit this, then most likely the received symbol will be somewhere around here. If you transmit this, then again, based on the probability, your receive symbol is going to be somewhere here. Right? Again, this is based on the probability. It's not going to be guaranteed, but still based on the probability. So let's say, in that case, let's say you receive this point, and you calculate these two, right? Based on that, eventually you're going to make a final decision. What's going to be your final decision in this particular case? H0 is going to be your final decision, H0, because you receive this point here, right? Always. So that's based on how you calculate this. So this probability is calculated based on the distance. Okay, that step is a little bit missing because that part is a little bit complex. So I'm not going to introduce that because that's a little bit complex. You're going to have some exponential equation and things like this. But simply speaking, let me go to the conclusion. The conclusion is that you're going to calculate these two. But this probability is based on the distance. So simply, you're going to compare this distance and this distance, and which one has a smaller distance. That is going to be the decision. So smaller distance means larger probability. Okay? This smaller distance means larger probability. Okay? And we are going to looking for a larger probability in our case. So in this particular case, H0 is much smaller distance. So this one has a larger probability. Therefore, our decision is going to be H0. That's simple as that. Let's take a look at another example. Let's say you receive this point. That's my S in this case. My S. What's going to be your final decision? H1 is going to be final decision in our case. Why? Because this distance and this distance, you just compare that. This one is smaller distance. Smaller distance means this one has a larger probability. If this one has a larger probability, then based on this rule, your decision is going to be H1 hypothesis. So H1 hypothesis in our case is going to be 1. So eventually your final output is going to be 1. That's how you do that. Okay? So this probability is what you're going to calculate based on the distance. And that's the story, whole story. So summarizing that, our original goal is to calculate this, but this one is very difficult to calculate. That's why in both sides, you're going to use the base rule and convert this one into this way, and then cancel out. We're going to make a simplification And also we assume that half and half, equal probability between H0 and H1. Once you make these assumptions and simplification, you're going to change this into that. So once you go to this, what you're going to calculate now is to calculate the probability of this one and this one. And these two probability are based on the distance. So eventually the conclusion is when you receive some point, let's say you receive that point. What are you going to do? What you need to do is simply measure the distance. Okay? And your decision is going to be the one with the closer distance. Simply that's going to be your decision. Once you make that decision, once you make a decision based on the distance, then let me redraw this picture. Once you make that kind of decision, we have this is S0, this is S0, H0, here is H1. So once you make decision based on the distance, then where is the decision area? Where is the decision making area? All of the right side would be the decision block, decision area for H0. Because let's say every point, every received symbol in the right side, let's say you receive this point. Your decision is going to be H0. Here, again H0. Here, again H0, right? So every point that you receive in the right side, right half plane, would be H0. That's the decision you're going to make, right? What about you receive a symbol on the left-hand side? All the symbol that you receive on the left-hand side would be H1. Okay? That's how you make a decision. Okay? Based on the distance, right? That's the finally that's the decision-making block. Decision-making rule, eventually. Okay. So that's the whole story of decision-making block. So the idea here is, again, we are talking about hypotheses and making a symptom or data, but in this case, what you're going to do is sometimes you can have many hypotheses. In our case, we have only two hypotheses. 0 or 1, because it's a binary system. But some other times, you can have more hypotheses. For example, let's say we use QPSK. In this case, we are using BPSK, so we have only two. Now, let's say we have a QPSK modulation. If you use a QPSK modulation, you know that constellation plot, we have 4 of them, right? Here, 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 here. In this case, you need to have 4 hypotheses because you can make out of these 4 decisions, right? So hypothesis number of hypotheses would be the number of decision you're going to have. Okay? So this H can be as many as number of symbols in your modulation. So anyway, either H is going to be only 2 hypotheses or 4 hypotheses. Anyway, what you're going to do is you're going to calculate the probability for each hypothesis. If you have 4 hypotheses, like a QPSK case, what you're going to do is you're going to calculate this one, H2, H3. So you're going to calculate 4 of them. Okay? So that basically means that you're going to calculate hypothesis H0 given the received data, D. Okay? So you're going to calculate the 4 of them because we use QPSK, right? And you're going to calculate all of these things and then compare which one has the largest value. So that means mathematically you can write it this way. You're going to calculate all of the hypotheses given D, like 4 of them, for example, and you're going to choose the maximum value. Which one has the largest value? And then you're going to get that value. So that's your final decision. If this one, for example, has the largest value, like a PH1 given D, If this one has the largest value, your final decision is going to be hypothesis 1. Okay, that's what you're going to do here in this equation. Okay, we call this one as a maximum or posterior probability. We call that as a map. The reason we call it this way is that this probability that we have here, probability given H0 given D, this is posterior probability. Okay, this one. This one is a posterior probability. Posterior. Okay. Posterior. Posterior probability. So we are going to calculate two different posterior probability. H0, H1, right? We're going to calculate this posterior probability, and choose the maximum out of these two. So that's why we call it as a maximum a posteriori probability. And this rule is, we call that as a maximum a posteriori decision. So that's called a map. Simply speaking, we are calculating this probability for each one of them and choose the maximum one. So that's what that means as a map receiver. Okay. Yeah. Okay, so we can continue next time.